for the presentation of the day. We have Mr. Petar Korponaic with his topic, hands-on quantum computing. If anybody has any questions, they can raise their hand whenever Mr. Petar allows it, and we can make this interactive because there's not a lot of people. You can have the podium, Mr. Petar.
Thank you for the introduction. And hello, everyone. Thank you for joining. My name is Petar Korponaic, and I'm from Quantastica. I'm founder of Quantastica. Quantastica is quantum software startup from Finland, Helsinki, Finland. I'm originally from Serbia, and I'm sitting in Serbia, in Subotica, Serbia. And today we will talk about quantum computing. And I prepared some presentation for you, so let me share my screen. Okay, so what is the plan today? I split this presentation in three parts. In first part, we will have a brief overview of quantum computing. In some previous conferences, I realized that people are not familiar with quantum computing, as I expected. Some people ask me, do quantum computers really exist? I was surprised with questions like those. So I decided in this presentation to give you overview of why do we need quantum computing at all? What is quantum computing? Where are we now with quantum computing, and so on. And then I will have a quick introduction to quantum programming, or how to say more about quantum software. I will not go into deep details, and I will not go into quantum physics and mathematics behind. I tried to make some very light introduction to quantum software. I hope that I succeed. We will see later. So this should be understandable, or how to say, easy to understand to people who are familiar with classical computing. So this should be I mean, easy, not too how to say, too deep, too quantum, more classical. And in third part, we will make one simple quantum program. We will really not do anything fancy. We will not try to calculate some complex things. We will do something simple from zero to quantum program, and to see how to integrate that quantum program into classical software. So this is plan for today, and let's start. So part one is a brief overview of quantum computing. Now, first to say, what is motivation for unconventional computing? Before talking about quantum, what is unconventional computing? So we have problems. Every industry and every science actually have problems which are computationally expensive. Problems that are hard to calculate, and we, humankind, we are in front of the wall. So human progress is in front of us. There is a wall which is called computational power. So in order to move forward, we need to solve some computational problems that are unsolvable with classical computers. Or let's say inaccessible to classical computers. And some of the problems are so complex and so hard that it was mathematically proven that some problems will never be solved on classical digital computers. So in order to move forward, to make significant, how to say, impact in every industry and in science, we need to think about other way to compute. So we need to think about unconventional computing. And one of approaches to unconventional computing is quantum computing. So quantum computing is one of unconventional ways to compute and to possibly reach problems or solve problems that are unsolvable for classical digital computers. So this is one motivation, maybe most important motivation, but there is also other motivation, which is to perform what classical computers can do faster or with lower cost or with less energy consumption, which could be the same thing, and or with better quality or better precision. So even if we reach that, to compute better or faster or cheaper than classical computers, this is already improvement. So unconventional computing is trying to do that. There are multiple approaches to unconventional computing. There is biocomputing using bacteria to compute. There is many different approaches, but quantum computing is what we do and what I do, and with what we are talking about today. So let's continue. What is quantum computing? Quantum computing is a use of quantum mechanical phenomena, which we usually, which we found in elementary particles, to perform computation. Now, so this is joint of quantum physics and computer science, some joint. And in this slide, in these pictures, you can see actual quantum computers which are in production. At the left side is Google quantum computer, which is a superconducting type of quantum computer. There are multiple approaches to quantum computing, and one of approaches, and maybe most popular approaches, is superconducting. And at the right side is ionic, ion trap quantum computer, which is different approach to quantum computing, using different technology to perform the same, to perform the same thing, but different technologies. I put these pictures only for you to understand that the quantum computers do really exist, and not only that quantum computers exist, quantum computers are available in a cloud. So you can use a quantum computer in AWS, Google Cloud, and AWS, or Microsoft Azure, and so on. So quantum computers are generally available. Even IBM even have free quantum computers, so you can use quantum computer for free as well in IBM Quantum Cloud. So quantum computers do exist. This is reality, and let's see what let's see more about quantum computing. Now, what is potential? What is at least theoretical potential of quantum computing? In this picture, you can see different complexity, classes of complexity. So we have constant complexity, which is at the far right, at the right side, which is easiest to solve problems with constant complexity. Then going to the left, we have more and more complex problems. Exponential problems are most complex, or we even have more complex than that, but it's not on this picture. And what is potential quantum computing? So you can see a few quantum algorithms, most popular quantum algorithms, which in this picture is shown what is the speed up of those quantum algorithms. For example, this Deutsche Josa quantum algorithm is most extreme example, which can theoretically can perform some or can calculate problem which has exponential complexity in constant time. So this is extreme speed up. And we have less extreme examples, right, like Simon's algorithm, quantum Fourier transform, Shor's algorithm for factoring numbers, or period finding algorithm. Anyway, so you can see that quantum explanation of this is that classical computers need exponential time to perform some problem, and this is the best we can do, the best algorithm we have has exponential complexity, and quantum computer can do it faster or in less time. So this is potential of quantum computing. Now, just to be sure that if somebody raise hand, would I be able to see it? Anyway.
I can see if somebody raised their hand, so
Okay.
I'm following.
Okay. Let's see. Okay, so impact could be huge. Now you can understand that impact could be huge, and will affect many industries, almost all industries. And in this slide, I gave only few examples. So this is not a full list. There is in healthcare, there is possibility to find to discover new drugs, for example, personalized medicine based on genetics, genetic, in chemistry we have possibly discover new materials and new chemicals and so on. So in every industry, for example, in the energy sector, maybe we can find new energy sources. Maybe we can solve some old problems like fusion energy. Maybe we can make more efficient batteries for electric vehicles and other uses. So quantum computing or unconventional computing, not only quantum, but we are talking about quantum computing, is promising that some of that in these industries, some very hard computational problems will be solved, and that industry will go forward, and we will have more progress. So we human will move forward with technological progress. So this is impact which could be huge, and because that industry is started preparing. Let me switch to this mode. Okay, so industry is preparing already, and I assembled only a small list of companies who are already experimenting with quantum computing. And I try to put for in healthcare, you can see familiar names here in this list. And those are mostly large companies, giants, who have budget for quantum research and I mean for alternative approaches to computing. And you can see that those companies are experimenting. Some of those companies are using external providers of quantum services. Some companies have own internal quantum computing teams. And we Quantastic participated in BMW Group and in Airbus some challenges that they published and so on. So companies are preparing. So this is reality. And now, so we have, let's say, we have customers, we have companies who are preparing, and we also have providers. So who are providers? Providers are, you can guess, big tech like Google, IBM, AWS, Microsoft, and so on. but also startups. There are startups who built their own quantum computers, and not only hardware, not only computers, but they also some of those startups have cloud, have quantum computers available in the cloud. Some of those startups are offering services, quantum, quantum software, quantum algorithm development, assessment of possibilities of quantum computing in companies and so on. Quantastica is one of those companies. I put it here. I almost forgot it to put it here. So Quantastica, most important, is here. Okay, let's continue. So we have customers, we have providers, but there is no quantum advantage yet. So what is quantum advantage? Quantum advantage is a point in which quantum computers can perform something faster, or with lower cost, or with less energy, or with better quality of precision than classical computers. So currently, quantum computers cannot do anything faster and better than classical digital computers, unfortunately. But quantum computing is still developing field, and we don't have yet, we didn't reach that point in which we can say, okay, now if you want to perform something faster, use quantum computer. No, currently your company, if you are from industry, your company can start preparing, can start assessing what is what could quantum computing, what benefit your company could have from quantum computing in the near future when quantum computers reach the quantum advantage. And so this is reality. So there is no quantum advantage yet, unfortunately, but it is developing in fast pace. It's moving forward very fast, and I not only believe, I'm sure that quantum computing will soon become important part of every company's operations. Okay, now, so why is that? Why we don't have a quantum advantage yet? The part of the problem is quantum hardware. So quantum hardware is imperfect. Why is that? Because we are trying to control quantum mechanical effects or quantum mechanical phenomena, let's say, which is not only strange and not only small, and it itself is unexplored. It's not fully explored and understood by us. And we are trying to very precisely control those elementary particles and interactions between them. So this is very hard, and quantum hardware, if we can call that hardware, you know, but quantum hardware is currently imperfect. We have noise. Noise is maybe the biggest problem at the moment. Noise. What means noise? Means that quantum computer returns results which are not accurate. Quantum computer don't return what you expect, but it returns noise. Qubit is a basic unit of quantum computation. Number of qubit is a measure of how powerful is quantum computer. This is not, of course, only measure, but this is something that we count, and the more qubits, the better. But qubit count is problem, and more qubits we have, more noise we have. So this is not easy. Qubit coherence. In classical computers, we have bits, and when you set bit to 1, it will stay 1. As long as computer has power, it will be 1. So there is no, the classical bit will never change if you don't change it. I mean, if software don't change it, it will stay in the same state, but qubits lose their state by time. So it's very hard to keep qubit in a steady state for a longer time. This is qubit coherence or decoherence. Then we have connectivity. In order to perform computation, we need to have connections between qubits. So inside, like in classical computer, we can use multiple bits for computation. In the same way, we need to use multiple qubits for computation. And because technology, how quantum computers are or quantum processors are made, not all qubits can talk with each other. So this is also a limiting factor. We have gate fidelity. Gate is instruction of a quantum computer, and when you perform some instruction, you expect that instruction really to happen, but it doesn't happen exactly what you ask quantum computer for. It produce some error. It produce something different than what you ask quantum computer. So we have there are multiple problems with quantum hardware, but quantum hardware is not the only problem. This is only part of the problem. The second part of the problem is quantum software. Now in quantum software, because quantum computer is totally different from classical digital computer, not only hardware, but also software. It's completely new paradigm. There is no binary logic. There is nothing that we know about computing or classical computing doesn't apply to quantum computer. So because that this space of quantum computation with complexity theory related to quantum computation and so on, everything is very unexplored. We are in early days of that, and research is done in that direction. And we have only small list of promising quantum algorithms. We have many quantum algorithms, but most of those algorithms are not scalable to practical sizes. Now, for example, in this slide, I put only few most popular algorithms, like Shor's algorithm, which is algorithm for factoring, which helps with factoring numbers and break security. Grover search, quantum phase estimation, variation quantum eigensolver, quantum approximate optimization algorithm, and so on. And in this picture, you can see scientists. You can see Bell, Peter Shor, Love Grover. And so those scientists are so these algorithms, the quantum algorithms that we have today are mostly discovered by greatest minds of our ages, how to say, of our time. And because quantum programming quantum computers or making quantum algorithm is much more challenging than making classical algorithms for classical digital computers. And for that reason, this field is very unexplored. There is a lot of space for innovation and for improvement. This is why quantum computing is exciting, because we are living in times where we have where we can join, contribute, and really move forward the technology. So when you are researching or working in quantum computers, you are actually at the front of technology. You are at the front, at the bleeding edge of technology, where humankind reached today. So second part of the problem, one part is hardware, second part is software, and not only algorithms, there are also a lot of research is done in error correction, because I said that quantum hardware has noise, and one of the way to how to say, to beat the noise is to do software error correction via software, and so on. So there is a lot of space for improvement in quantum computing, and it is exciting, I can say. Now, what we need in order to so quantum hardware will be solved, I believe, and every year, maybe almost every month, we have better and better quantum computers. A lot of investment is a lot of money is invested into quantum computing, and large technical giants like IBM are doing a lot to improve quantum hardware. It will happen, and but in software, of course, it will happen in software as well. But we are talking here about software. So what we need to move forward, even if we today have perfect quantum computer, noiseless and a lot of qubits and so on, what quantum algorithm we will run on that computer? How we will solve some of industry's hardest problems on that perfect quantum computer? What we need winning quantum algorithm. And what is winning quantum algorithm? This is quantum algorithm which can solve some real world problem, because maybe you can read, if you Google around, you can read that scientists perform some computation which takes 10,000 years for fastest classical digital supercomputer. They done that on quantum computer in 3 minutes. But the problem that they solved is not a practical problem, is not something that is of practical use for anyone. I mean, nobody will give you money for solving that problem, in other words. So in order to I mean, quantum computer to be useful, we need to solve some real world problem, something that is useful to science or for industry. Then we need algorithm which will efficiently utilize quantum resources, because we are limited. We have noise, we are limited with number of qubits and so on. So we need efficient quantum algorithm, robust to noise, scalable to practical problem sizes, because many of quantum algorithms, even some of those of these quantum algorithms are not scalable. You can run quantum algorithm in small scale, something that computes solves some problem which can you solve with pen and paper. But if you as input increases, the quantum algorithm is not scalable. Not because hardware, but because quantum algorithm itself is not scalable because some other limits. Because requirement of very, very precise control of qubits and so on. So simply many quantum algorithms are not scalable. And we need scalable quantum algorithms. And also we need quantum algorithm which is implementable on current quantum hardware. Not something that, I mean, not algorithm which will wait for some future quantum computer, but algorithm which you can run today on IBM or Google or other quantum computer. So this is, we need winning quantum algorithms, and this space is very unexplored. There is a lot of space for improvement, and this is what we, at Quantastica, what we do. We are doing research I mean, we have tools which helps with research on quantum algorithms. And where are we now? So this is least popular slide, and this is slide that people advise me don't show this to people. But I have to show. I mean, this is reality. This is where we are now. So what quantum computers can do? How powerful are quantum computers today? I show three popular problems that many industries share. One is traveling salesman problem. This is famous problem. This is NP hard problem, I guess that everybody knows what is traveling salesman. But so we have, let's say, we have multiple cities, and your job is to visit all cities and to come back to starting point and to visit every point only once. And what is the shortest path? So in which order to visit all points so what is shortest path between cities? And this problem has high complexity, and quantum algorithms promise super polynomial speed up. And what is the largest traveling salesman problem ever calculated on quantum computer? This is problem of 5 cities. So I give you 5 cities, and you tell me what is the shortest path. And this is something you can do on pen and paper. So you don't really need a computer, not to tell a quantum computer, but this is what quantum computer can do today. At least with this algorithm, with this quantum approximate optimization algorithm. There are specialized quantum machines which are specialized for combinatorial optimization problems, like D-Wave quantum computer. D-Wave can do much better. But here I'm talking about universal quantum computer, which is quantum computer which is produced by IBM, Google, and these mainstream companies. Something that is most similar, let's say, to classical computers in terms that it will be universal use. We will be able to solve many different problems with the same computer. And when talking about universal quantum computer, IBM quantum computer, you can solve traveling salesman problem with 5 cities only. So this is the bleeding edge. This is the latest where we are now. Of course, this is improving every day. Maybe I put this data few weeks ago. Maybe there is something new happened in meantime, but it's improving. But this is where we are now. Integer factorization. People are afraid that quantum computers will break encryption. And some encryption algorithms are based on factoring on number factoring. Now, if you want to break encryption, you need to factor large numbers. So I give you large number, large integer, and your job is to tell which 2 prime numbers to multiply to get that large input number. Some balloons are safe here. Okay. Now, in order to do that, there is no algorithm. There is no efficient algorithm. There is no efficient classical algorithm. If number is large, there is no. I mean, fastest supercomputer will work for million years to find factors. And this is why encryption is strong. This is why we use that for data security on the internet. Now, quantum computers are promising to solve this problem more efficiently. And people are afraid now quantum computers will break encryption. And not people, I mean, governments are afraid of, and militaries are afraid of that. Now, to tell you what quantum computer can factor. So quantum computer, largest number factored on universal superconducting quantum computer is number 21. So quantum computer can tell you that 3 times 7 is 21. This is something that you can do. You don't even need a pen and paper, and not to mention computer and not quantum computer. So this is where quantum computer is now with factoring numbers. So you are safe for now, don't worry, but you need to be prepared. because this is every advancement in quantum computing is going exponentially. So next number will be, you know, maybe 5-digit number. Next number will be 10-digit number. So this is going fast. This could be fast. So maybe we can have in 2 years, maybe we will have a computer which will factor large numbers. But for now, today, this is what quantum computer can do. So it's better to be prepared, but don't panic. And molecular simulation, this is actually original use of quantum computer, because Richard Feynman, which is a famous physicist, who was, how to say, supporter of, or how to say, one of the fathers of quantum computing. He says that the nature is quantum, and we need to use quantum machines if we want to simulate nature processes. And molecules are natural, and molecules are, how to say, quantum. And in order to simulate molecule, we need quantum computer. And this is, how to say, original idea why we need quantum computer. And today, for calculating energy, minimal energy of molecular bond. So this is energy of bond between atoms in a molecule. I'm not computational chemistry is not my field, but in order to calculate that energy, the more atoms you have in a molecule, the complexity grows drastically. So I'm not sure if this is exponential complexity or is factorial, or who knows, but its complexity grows drastically. And quantum, and for example, it would be great if we can simulate DNA molecule. And by simulating DNA molecule, we would be able to perform miracles in terms of cures, new drugs, and who knows what we can do with by simulating DNA. But DNA is giant molecule, maybe largest molecule in the universe. If not, I'm not sure. Anyway, the largest molecule which is simulated on universal quantum computer is this methyl fluoride or fluoromethane. So this molecule has 5 atoms. So this is 5-atom molecule, and this is state of the art. This is what quantum computer can simulate. It cannot simulate DNA, not yet. It cannot simulate proteins. There is methods for protein folding, which is Google's AlphaFold or something. This is machine learning approach, which is much more powerful than quantum computer today. But as I said, field is advancing very fast, and it's possible that in near future we will be able to simulate much more complex molecules, and maybe one day, because there is no theoretical obstacle. So theoretically, classical computers will never be able to simulate DNA molecule, but quantum computers theoretically will be able to simulate DNA molecules. So who knows in the future, or I mean, who knows in how far is that future, or how close is that future, but we could possibly have very powerful simulations of molecules, which will open many new possibilities and technological advancement. Okay, so this is about quantum, brief introduction to field of quantum computing. Now let's talk about quantum, more specifically about quantum software. Let's see how quantum computer computes. Let's demystify that, because I said that quantum computer is very different than classical. So let's see how it works. I will try to explain in simple words. In this picture, you can see how classical computer and quantum computer will work together. Quantum computers will not replace classical digital computers. Quantum computers will be something like GPUs that we have today. Quantum computers will be some kind of coprocessors, which will perform only computations which are suitable for quantum computer, because not every problem is suitable. Some problems are much easier and faster and more accurate to perform on digital computer. So we will not do everything. You will not watch YouTube on quantum computer. I mean, but you will calculate maybe some molecule or some, you know, combinatorial problem on quantum computer, but not watching YouTube or I don't know, Netflix. Anyway, so this is classical and quantum computer will work together. And in this picture, at the upper side of the picture, you can see classical computer. So this is what we have currently, classical computers. Bottom part is quantum computer. And we have some data, some input data we have stored in a classical computer. It's in a memory of classical computer. It's on file, on disk, maybe it's on internet or somewhere, but we have some data in classical computer. And we want to perform computation to get output data. So output data in our classical digital computers. And to perform that, we need to encode that data into quantum computer, because in quantum computer there is no really input port where you can simply write data. Quantum computers has state, quantum state, which is at the beginning it's initialized in so-called zero state. When you turn on quantum computer, it's in zero state, and then only way to enter data into that state, to put data into state, is to perform it, is to execute program, quantum program. And so in order to encode data into state of a quantum computer, which is this point, you need to encode. Encode means create quantum program which will produce quantum state, which will have data, our input data, encoded into it. So quantum program which will transform zero state into prepared state. This is what we need to do in this encoding process. And then when we have prepared state, when quantum computer contains, state of a quantum computer contains our data, then we execute main quantum program. I mean, everything executes actually in single, how to say, in single shot, but I put this intermediate state for clarity. Now, main program executes and transforms our input or prepared input state into final state. And then that final state is measured. In quantum computer, we say measure. We don't read, because in classical digital computer, you read bits, you read bytes from your memory. But in quantum computer, we cannot access even that directly. We need to sample from it. So we perform measurement. And from that measurement, with many measurements, we make statistics, we sample most probable result, and we decode that, and then we have output data. So this is how quantum computer and classical computer and quantum computer will work together. Okay. When talking about this quantum state, let's see what is that quantum state. So that quantum state is something equivalent to memory of a classical digital computers. In quantum computer, we have quantum state, and this state is just a mathematical abstraction. So quantum computer, it doesn't have some memory in classical sense where it stores some numbers. The state of a quantum computer is actually a mathematical abstraction of probability of probabilities of a state in which we can find that quantum computer, or what we can measure from it. And that state of quantum computer can be described with a vector. So this is vector of this is vector of complex numbers. In previous conference in London, I tried to explain this part, what means that that vector, and it turned that my presentation took 2.5 hours instead 1 hour. So I will not try to do that. So quantum, for you, it's enough to understand that state of a quantum computer is vector of complex numbers. From software perspective, this is enough. You don't need to understand quantum physics to program quantum computer. It's better if you understand something, but you don't need to. Like you don't need to understand how motor of your car works in much details. You need to understand which pedal to push and you drive. So you don't need to understand quantum physics really, but important to understand is that state of a quantum computer is vector, and size of the vector is 2 on n, where n is number of qubits. We says that quantum computer has qubits, which are basic units of quantum computation. And if we have 3 qubits, so if we have 1 qubit, then this is 2 on 1. So we have vector of 2 numbers. So this middle part marked with this letter psi. This is Greek letter psi. This middle part is actually vector. And 2 qubits has 2 power 2, which is 4 elements, and 3 qubits has 8 elements, and so on. And 2 on 272 is approximated number of atoms in the observable universe. So state of a quantum of 272 qubit quantum computer could be described with a giant vector, which is which has as many elements as number of atoms in the observable universe, which is of course something that we cannot store into any computer. But you need to understand that state of a quantum computer is very very large. It's a giant state, and what these numbers mean, let's try to just to explain that. So elements are complex numbers. We have real and imaginary part, and sum of all elements, if you square, so absolute value squared of each element when added together, so sum of all elements is 1, is always 1. So these vectors are unit vectors. Why? Because these elements are actually probability. So for this 1 qubit, we have probability that we will find qubit in state of 0, 50% probability in this example, and we have probability of 50% that we will find qubit in state 1. So our state actually looks like this. This 0.707 something when squared will give you 0.5. So 50%. And so because total probability is always 1, always 100%, then this is why these vectors are unit vectors. And in 2-qubit quantum computer, we have 2 qubits, and we have probability that we will measure both qubits 0. So when we index, when we look at index in binary form, 0, 0 means probability. So what is the probability that we will find both qubits in state of 0? Because from qubit we can read only 1 or 0. So at the end we read binary from quantum computer, but inside it's completely different story. So the probability that we will find both 0 is, in this example, is 25%. Then first qubit 1, second qubit 0, 25% again, then first qubit 0, second qubit 1, and so on. And with 3 qubits, so we have for each combination of qubits, we have probability. And this is these 3 vectors are just random examples that I put. Vector or state of a quantum computer can be anything, any vector, as long as the sum, the total sum of all elements is 1. This is most important. And so let's finish with this. So state of a quantum computer is a unit vector of complex number, or vector in complex vector space, in Hilbert space. But let's continue. So this is state vector, and I gave more examples here. So we have 0 state, 3 qubit 0 state. This is state that I mentioned in few slides before. This is 0 state is 100% probability that we will find all 3 qubits in 0 state, or that we will read 3 zeros from 3 qubit quantum computer. So 3 zeros. So first element is 1, and all other elements are 0. So this is 0 state. Then we have some Gehazi state. This is a hello world of quantum computing. So this is maximally entangled state. We have 50% probability of all zeros and 50% probability of all ones. And all other states are 0% probability. So this is just an example of state vector. And we have some random state, which I put just nothing special. And we have just for you to see that vector or state of a quantum computer can have any state as long as sum of square elements, absolute value square is 1. Okay. Now our goal when performing computation, let me go back to this slide. Our goal is to somehow encode this input data into vector. So let's say that you have number, or you have what is your input? Maybe your input is picture, sound file, video file. I don't know, vector, matrix, whatever is your input. You need somehow to encode that data into vector, into unit vector of complex numbers. So this is your goal, how you put data into quantum computer, encode it into vector of complex numbers. Now let's go next slide. Measurement. We have, let's say that we have quantum computer in some state. Important to say is that we cannot directly observe, so we cannot read these values directly. All we can do is to sample. When we measure, so we measure state of quantum computer, and outcome will be 1 bit string of 3 bits in this case, because this is 3 qubit quantum computer. We will get only 3 bits out of it. And which 3 bits? When we do this again, so you can see that the highest probability is this element, 0, 1, 1. It has 33% of probability of reading. And you would expect that when you measure, when you sample, I mean, when you measure state of a quantum computer, you will read this number. But this is not always the case. You will get this number most often, most frequently. So when you perform measurement 100 times, you will get 33 times this outcome, but 29 times this outcome, and so on. This is why I put on this picture, I didn't show the most probable value, but some other value. You can also sometimes get this 000, which has very, very small probability. But anyway, so you cannot read directly from state from quantum computer. You can only measure one. And when you measure, you destroy the state of a quantum computer is destroyed. And then you need to, again, to initialize quantum computer, run your quantum program, produce your state, and then measure again. And then you will get other number. And then you perform these thousands of times, and then you sample, and you actually statistically get these numbers. So you cannot directly write into quantum computer, and also you cannot directly read. And this is not engineering problem. This is not engineering obstacle. This is not that we didn't find a way. This is a fundamental principle of quantum mechanics. So you cannot, you cannot directly read the quantum state, and you cannot directly, directly write into this state, because this state actually doesn't exist. This state is actually just a mathematical abstraction of probability of a quantum system. Let's continue. So now, because we learned that state of a quantum computer is vector, and we need somehow to mutate that vector. So we need to perform computation, and because initial state. Let's go to this slide. So initial state is some vector, and when we perform quantum program, new state will be again vector. So this state is the same quantum computer, but in time, later in time, we have different state. And that state is actually mutation of initial state, and because state is always unit vector, this transformation between two quantum states we can describe with matrix, and not any matrix. This matrix is unitary matrix. Unitary is property of a matrix. If you know linear algebra, you know, and now quantum program. So equivalent of a quantum of a memory of a quantum computer is quantum state, and equivalent of a quantum program is matrix. So we have vectors and matrices. So quantum computing is is all about linear algebra. Linear algebra is everything is your everyday, how to say, your everyday, your head is linear algebra when you are playing with quantum computing. And yes, so let's go forward to this last slide. Now we have some initial state. In this case, this is zero state. I draw 2 qubit state here because space on the screen, only because that. So we have 4 element vector, which is 2 qubit state. We have quantum program, which can be described by a 4 by 4 unitary matrix. Why 4 by 4? Because we have 4 elements in a vector. So dimension of matrix must be the same as dimension of vector. And when we make a dot product of state with a matrix, we get final state. We get new state, which is in this case, this is Bell state or 2 qubit GHZ or Bell state, which is fully entangled state. So this is just one example of quantum program. Zero state in quantum computer initialized, we perform quantum program, which is matrix, and then output is final state. This is hello world of quantum computing. This is how quantum computer works. Now, this quantum program Now, quantum computer cannot perform arbitrary transformation. It cannot perform any matrix, how to say. Quantum computer has a instruction set. It can perform only few, usually 2 or 3 matrix transformations. And we need to disassemble, how to say, to decompose our quantum program, our matrix that we want to perform. We need to decompose it to instruction set of our target quantum processor. And in this example, I split this matrix into decomposed this matrix into set of matrices. So we have two 2x2 matrices, which is, and in quantum computing, matrices have names. We have names for matrices. So, for example, this matrix is called Hadamard. This is identity. Of course, everybody knows identity matrix, and this is controlled knot matrix. So I decompose this quantum program into 3 matrices, into Hadamard, identity, and C-naught. And Hadamard multiplied with identity, but this is a tensor multiplication. So this is not dot product. This is a tensor product of matrices, and we result is 4x4 matrix, which we then dot multiply with C-naught matrix, and the resulting matrix is our quantum program. So our quantum program is decomposed to 3 smaller matrices. And because drawing or writing these matrices is very uncomfortable. So if imagine that we have thousands of these instructions of these matrices, so it will be hard for human to follow this. So we have a shorter way to describe or to draw or to write a quantum program, and shorter way is actually quantum circuit. So quantum circuit diagram. And in this picture, we have these horizontal lines are qubits. We have 2 qubit quantum computer. So the matrix of entire quantum program is 4x4 because we have 2 qubits. So 2 on 2 is 4x4 matrix. And we have these symbols are actually matrices. So every matrix have a name, and also every matrix have a symbol. Not every matrix, but few matrices, so-called quantum gates. So these matrices are actually called quantum gates. And in this picture, we have Hadamard, which is here, described here. So Hadamard on first qubit. Then identity is not shown in diagram. We don't need to show because identity doesn't have any effect on a qubit, but it actually extends our Hadamard to be 4x4. This is why I need to put it here. But on diagram, we don't need it. And we have C-naught, which is this symbol. It's 4x4. That means it spans 2 qubits. This is why it's spanning 2 qubits. It's connecting 2 qubits. This symbol is knot. So this is controlled knot gate, and this is its matrix. And now these circuits are handy for us humans, but are not handy for machines. So in order to put, so we can draw this circuit, but in order to enter it into computer, we need some quantum programming language. And there are multiple quantum programming languages. One low-level quantum computing language is quantum assembler, named OpenQASM. And open chasm is actually a way to express these diagrams, but programmatically. So we have some header file. We have quantum register. QReg is quantum register. So we have named Q, which has 2 qubits. So this is Q0 and Q1. So we have 2 qubits. These horizontal lines are qubits. And we have classical register, CReg, classical register named C. So this register is C register, classical register, where we will store result of our computation in that register, which has 2 classical bits. Then we have H, which is Hadamard. So H matrix performing on qubit 0. So on qubit 0, H. And we have CX between qubit 0 and qubit 1. So this is controlled action or controlled knot between qubit 0 and qubit 1. And we have measurement. So we measure qubit 0 and store result into classical registers, bit 0. And in qubit 1 or in quantum register Q, qubit 1, we store measurement result into classical register in bit 1, second bit of classical register. So this is one simplest quantum program. And quantum assembler is usually is useful for moving, exporting and importing quantum circuits between different frameworks. But usually people use Python for programming quantum computers. So there are frameworks, Python frameworks for programming quantum computers. Most popular is Qiskit, which is Quantum Information Science Toolkit by IBM. But there are also others, Cirq by Google, PyQuil by Rigetti, which was Fantastica's partner, and so on. Anyway, there are different quantum frameworks, but they are performing very similar things. So the goal is to encode somehow this into quantum computer. So we have some input statements. We describe quantum circuit registers, the same as we did with quantum assembler. We have quantum register 2 qubit and classical register with 2 classical bits. We add that registers to quantum circuit. Then we perform quantum circuit, perform H, which is this H, on qubit 0, and CX on between qubit 0 and 1, and then measure. Very similar, very same. And here is where we execute quantum computer actually. So we execute this quantum circuit on backend. And in this example, backend is simulator. There are quantum computer simulators. You can simulate small quantum computer on your classical computer. And you perform 1024 in this case shots. So you repeat this 1024 times, and every time you measure, and then you get sampling results and as output, which I print here. So this is just a small hello world quantum computer example. And this is how you program quantum computers. So you are dealing with matrices. So your goal is to encode your data into state vector, into state of a quantum computer by performing multiple matrix transformations of 0 state vector. And then when you have your data encoded into state, you perform more transformations. And result is final state, which you then measure and decode output data out of it. So this is how quantum computer computes. I hope this is understandable. I hope this is not too confusing. But let's continue. So important to say is that there are 2 main branches of quantum algorithms. We have quantum-only algorithm, which I described in previous slides, where you encode data into quantum state, execute quantum program, and read output of computation from quantum state. This is one approach. And there is another approach, which is popular between data scientists and then people who are performing machine learning, where quantum computer is actually used as a machine to perform matrix vector multiplication. Let's banalize that this way. So we have quantum program which is parameterized. It takes parameters. So those matrices can have formulas, are not fixed, can be formulas. So by changing parameters, you are changing matrices. And so quantum program can be parameterized. And now you start with some initial parameters. You have some input data. And these blue boxes are actually classical computer. Only green box is quantum computer here. So data is not entering into quantum computer. Data is still in a classical computer, but we are searching for optimal parameters. With optimal parameters and with resulting quantum state, we perform some operation for example, by multiplying our input state with resulting vector or something. For example, we are searching for searching for eigenvector of some input matrix, and we change parameters of a quantum program as long as we find minimal eigenvector, which will give us minimal eigenvalue. And then when we find it, we return output of our computation, which is not from quantum, so from classical, but we are using quantum computer to find vector more efficiently only by changing parameters of a quantum program. And this by using classical optimizer, which is people who are familiar with data science are familiar with that approach. So this is two approaches. Those approaches have advantages and disadvantages. And some problems are some algorithms are, there's two streams of research in quantum algorithms. Some people are researching quantum-only algorithms. Some people are researching this hybrid variational quantum algorithms. We don't know which will win. Maybe both. Maybe I don't know. But if you ask me, I believe more into this quantum-only approach, because here there are many problems. Noisy, barren plateaus. It's very hard to optimize. There is many parameters. A lot of problems here. So I'm more for this quantum-only approach, because nature is quantum, not classical. But anyway, so let's continue. Let's continue because time is flying. Now I see that I have only 12 minutes more. 12 more minutes, if I understand well. So what are the challenges? Challenges is to choose real-world problems suitable for quantum computer, choose existing or develop a new quantum algorithm, efficiently encode data into quantum state, because data encoding itself is computationally expensive. And we need to find a good way or efficient way to encode our classical data into quantum state. So this is challenging. Then we need to efficiently compile quantum program for the target quantum processing unit. That means that we need to decompose that matrix that we want to get, the transformation that we want to perform. We need to compile it as a set of as small as possible set of quantum gates or quantum operations, because with every quantum instruction or with every that matrix that quantum computer executes, the noise multiplies. So you have more and more and more noise. So you need shorter and shorter quantum program in order to perform something meaningful to read result from noise. And we need to find a way how to efficiently decode data from the quantum state. And we need to see how to deal with noise. Now, this is challenges of quantum software, and we at Quantastica, we have a set of tools which can automate design of quantum algorithms. We have tool which can find quantum algorithm automatically from example data. So you provide us your data, and we from data we can reverse engineer quantum algorithm. We have tool which can perform that. And this algorithm is used by our first user, pilot user was US Department of Energy, who performed some elementary particle simulation experiment on quantum computer, and they find algorithm using our tool. Yeah, so this is what we do, not to do advertising. Let's continue with learning. So now, hands-on part. Now, I don't know if I really have time for this. Let me see if organizer can tell me. Okay, maybe he's not listening.
Sorry, can you repeat the question?
Okay, so question is how much time I have? Do I have time for third?
10 minutes are left.
10 minutes. Let's try to do very quick hands-on. A little bit get out of time. So yes, let me show you the simplest encoding scheme. The simplest way how to encode data into quantum state is binary encoding. There is many ways. So because you need to somehow to encode your data, your classical data, which can be arbitrary, any data set or whatever, into unit vector of complex numbers. And of course, you need to do that not directly, but indirectly by executing matrices. There is many ways to perform that, and there is not the best way, and this is object of research. So but easiest way to encode your data into quantum state is binary encoding. And if your data is integer, let's say in this example we will perform some factoring small numbers. We will make quantum program which will factor number using binary encoding. So we will not use Shor's algorithm. We will use our algorithm, which is ad hoc developed automatically by using our Quantastica tools, which is nothing revolutionary, nothing special, just to show you what is the principle of work. And we have a way, by using this binary encoding, you can make a quantum program for almost any function, as long as data, input and output data together are not large, because with size of data, this complexity grows exponentially, and you will not be able to describe those matrices in a classical computer, and our tool will not be able to give you result. But this is way how to make program for almost any function without greatest minds of our times. Only by using machine learning and computers, we can reverse engineer quantum algorithm out of it. And we will make exercise factor small integer. And let's continue. Time is flying. Okay, I have 6 minutes. It will not work for 6 minutes. So I will only say a few words about every slide. And in this slide, I showed how to encode binary number. This is number 5. Binary is 101. This is easy. You only need to perform X gate. So this X matrix, which is have 1 on secondary diagonal, and so X, identity X, is actually 101. And this is why it's very easy to encode binary data in a quantum computer, because the complexity is constant. So you don't need to perform anything fancy when converting your data into quantum state. So you only need to perform X, nothing, X, to encode 101. And the resulting vector, I show how vectors look. Okay, now you can also encode multiple numbers. For example, 1, 4, and 5. When looking at those numbers binary, we can have probability of 33% for each of the numbers, and we can store that all those 3 numbers into state vector. And for that we need more complex circuit. So this is not only like here. Anyway, then we can perform any truth table into vectors. If you convert input from truth into one set of vector and output into other set of vector, then you can perform, you have input vectors and output vectors, and from that point you can reverse engineer using our tool. You can reverse engineer matrix, unitary matrix, which will perform this transformation for every pair of vectors. You get the quantum circuit as output, and I prepared some coding exercise. I have some Jupyter notebook, but simply I have only 4 minutes, so I will not be able to do that. I'm very sorry for that. I'm very happy to continue if you are any other time. If you are, I'm always willing to talk with people. If anybody is interested, I'm very happy to feel free to contact me via email, and I can show you what we have, what we do, and what you can do maybe in your organization, and so on.